Hi everyone. So this is chemistry lesson 2, chemical equations, and what we're going to be doing in this lesson is going over the basics of writing a chemical equation. We're going to leave the balancing of equations for the next lesson. Okay, so just quick sort of tour here. So we're going to be looking at these kinds of things. So we have a balanced equation here, balanced chemical equation, and we have a word equation below that for the same reaction, and that's this reaction here, which is the reaction of alkali metals with water, in this case potassium. It's a bit of a tribute to Grant Imahara. If anyone has heard, he passed away a few days ago. He was one of the main people on Mythbusters, which was a great show for science fans and science teachers. So yeah, rest in peace. Okay, so we're going to start out with a quote that's going to come back to us later in this topic that's going to be important. This is Socrates, the old Greek philosopher that taught Plato, a disorderly mob is no more an army than a heap of building materials is a house. So basically, if you get a bunch of people together and give them weapons, even if you have a lot of them, it's not really an army if they don't know what they're doing. If you can imagine back in Socrates' time, people kind of, when they, at least in Greece, when they fought, they kind of did this kind of thing where you had, they call these soldiers hoplites, and they're not a disorderly mob, right? They fight in formation. If they are out of formation, they will lose their ability to fight very quickly, because when you're standing like this, one person can protect the others, right? One shield overlaps with the others. The spears that are up in the air prevent some arrow fire from having an effect. So in any case, having a bunch of something is not the same as having an organized unit, and that's true for a home as well, right? If you have a bunch of wood kind of just lying out there, even if you have enough wood to make a house, obviously that's not a house. The house requires the actual assembly of that wood. Might seem kind of obvious, but you're going to see how this applies to chemical reactions in a little bit. Okay, learning goals. We're going to look at what a chemical reaction is, or a chemical equation, what it represents in the real world. Can you take information and create word equations out of it? Or symbol equations. So symbol equations meaning things with chemical formulas like CH4 or H2O, kind of like what we saw on the intro slides. So basically, can you make word equations into symbol equations? Can you make symbol equations into word equations? And can we use these things called state symbols, which we're going to talk about as well. Okay, so terminology. Sometimes it's a little bit confusing. Often in grade 9 you'll hear about chemical change. If a chemical change happens, how do you know? And there's a whole bunch of signs that it's happened. Well, another word for a chemical change is chemical reaction. They are the same thing. So we're now going to be talking about chemical reactions, which are chemical changes. And so when you talk about chemical reactions, you have a reactant or multiple reactants. So your reactants are the starting materials in a chemical reaction. There might be just one. There might be more than one. And you have products. So these are the materials you end up with at the end of the reaction. So again, there might be just one, but there can sometimes be more than one. So what actually is a chemical reaction in the real world? And we've been talking about Bohr-Rutherford diagrams in our last, in our day 3. So how does it relate maybe to that? Can we use Bohr-Rutherford's diagrams to understand? So yeah, chemical reaction is what happens when you either break or form ionic or covalent bonds. So remember, when you have a metal and a nonmetal, you can make an ionic compound. They can react. The metal will lose electrons, the nonmetal will gain electrons, and you'll form an ionic bond. So this is actually a chemical reaction happening here. You have reactants, sodium and chlorine, and they produce sodium chloride. So you can see a bond is forming. The same thing can apply to molecular compounds like this one, CH4, which we call methane. You can see that the electrons are being shared. That's what this is showing you here. So you've got a covalent bond. So if you've ever heard of natural gas being used as a source of energy, if you've ever, say, maybe burned natural gas for whatever reason, sometimes this is actually done. Some stoves run on natural gas. So the burning of methane in a stove or in a Bunsen burner, if you've ever used a Bunsen burner, is a chemical reaction. So when you burn methane, you break the carbon-hydrogen bonds, and you form new bonds between carbon and oxygen and hydrogen and oxygen. So this is a type of reaction that we'll briefly mention later on. Okay, so baking a cake. If you think about physical and chemical changes from grade 9, think about how do you know if a chemical change has happened, right? What are the signs? Do you have a change of smell? maybe a change in color, maybe you see bubbles, right, if a gas is formed. It's irreversible, right, if you remember all those things from grade 9. So then baking a cake, would this be a chemical or a physical change? Well, the short answer is both. There's a lot that goes into baking a cake, right? If you're actually just mixing, say, flour and egg and other material in a bowl, if you're just mixing it together, that will be a physical change. But once you actually bake it, so I guess if you say the actual baking of a cake, that's a chemical change, right? There's no going back to eggs and flour and butter from this. And you can clearly tell that if you're baking a cake, it's going to smell very, very nice. You're going to have gases, right, if the cake's going to rise, for example. So this is a chemical change. It's, in fact, many chemical changes. Okay, so if you're baking a cake, you have ingredients. So you could think of these as being your reactants. And the cake itself is the end material, so the cake is your finished product. So you could write this as a chemical equation. Obviously, this is very simplified, right? You're not actually, there's many more ingredients than I just have on the left, so there's more than 3. But this is kind of the way you would write it, right? You list your ingredients, and you put plus signs between them. You put an arrow, and then you put the product. Okay? So when you're writing these kinds of equations, they come in 2 forms. They come in word equations. This is a word equation where you actually have the words, but they also come in symbol forms where you use the actual chemical symbols for an equation for elements and compounds. So sodium is written like Na instead of actual word sodium. Okay, so again, there's a couple of examples: word equation, symbol equation. Okay, so this is where our talk about houses and armies is going to come into play when we look at the rules for writing chemical equations. So the equation is read from left to right. So you start with your reactants on the left, your products on the right. The left side of the arrow always contains the reactants, as we just said. The right side contains the products. The plus sign is used as a substitute for the English word and. So in both the types of equations, you have a plus sign instead of saying and. And then this point here is don't use an equal sign. This is a very common mistake I've seen a lot where students will write because there's pluses, maybe they think because it looks like math, that there should be an equal sign there. But remember, a heap of building materials is not a house. A heap of chocolate and flour is not a cake. So lead 2 nitrate and potassium iodide does not equal potassium nitrate and lead 2 iodide. They're not the same. It's just that if you take these and expose them to certain conditions, they will make these. Just like if you take chocolate and flour and icing and eggs and you treat them a certain way, you can make a cake out of them, but they don't equal cake, right? Okay, practice question. Sodium metal is reacted with copper 2 chloride to produce sodium chloride and copper metal. Can you write this as a word equation and as a symbol equation? Okay, so I'm going to do this one. Maybe you can try and do this on your own very quickly, and I'm going to show you the answer in a Word document. Okay, so I'm going to go through it now. Sodium metal is reacted with copper 2 chloride to produce sodium chloride and copper metal. So we want to describe the equation using a word equation and a symbol equation. So word equation is pretty easy. So we're going to say sodium, plus copper 2 chloride. So plus means with or and, right, is plus. You're adding those 2 things together. Arrow, not equal sign, to produce sodium chloride and copper. So that would be my word equation, right? So this is my word equation. My symbol equation, you might know that these need to be balanced, but we're not going to worry about that right now. We're just going to write out the symbols just so you get used to seeing it. So sodium is just Na. Copper 2 chloride, maybe you know what that is already, but if you don't, make sure that you go to your periodic table of ions. So copper 2 is Cu2 plus. Copper 2 chloride, right? Chloride is 1 minus charge, Cl1 minus. So if you're going to use your crossover rule, that's going to be copper 2 chloride will look like that. and you're going to make sodium chloride. So again, you could go to your periodic table of ions, but you'll notice that sodium has a charge of +1 and chloride has a charge of -1. So they cancel out exactly. It's a 1-to-1 ratio, so you just put a 1 here and a 1 there, which we don't show. And copper metal will just be copper. Right? When you're talking about metals, if it says just the metal, that is just the element itself. So it's not like copper with a 2 or a 3. The places where you'll actually see 2s or, well, basically you'll see 2s are for some kinds of gases like hydrogen or oxygen. There is a way to remember it. I'll show it to you very quickly. Have no fear of ice cold beer. So hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. These chemicals all have a 2 after them. So if you have hydrogen gas, it's H2. If you have nitrogen gas, it's N2. Fluorine gas is F2, and so on. Everything else, as far as we're concerned, there won't be a 2. It'll just be Cu or Na or whatever else that we have. Okay, so let's go back. Okay, just some help here if you want some common English phrases for how you know you have a plus or an arrow sign. If you're given a description of something happening and you want to make a word equation out of it, that kind of goes with all these things, and that kind of goes with all these things. All right, last sort of major thing to mention here before going over a couple of examples is state symbols. So state symbols are used to represent the 3 states of matter that are common in chemical reactions, meaning solid, liquid, and gas. And there's another state symbol for things that are dissolved in water. So AQ stands for aqueous. That means that it's dissolved in water. So if you're thinking of sodium chloride, NaCl, NaCl can be solid or it can be aqueous. Solid NaCl is the table salt. Basically, it's that white material in salt that you put on your food. Aqueous NaCl is salt water. Okay, so whenever you see something as aqueous, think of that thing being dissolved in water. And we use symbols for all of these states in symbol equations, and that's what they look like. So if you see solid, you'll see that at the end of a symbol with an S. If it's liquid, you'll see an L. Gas, you'll see a G. Aqueous, you'll see a Q. So you get a little bit more information in a symbol equation than you do in a word equation, which is why chemists usually use symbol equations, although you'll occasionally see word equations. So example, we have aqueous iron 3 nitrate reacting with solid potassium metal to produce aqueous potassium nitrate and iron metal. Represent this using a symbol equation and use state symbols. Okay, so this example is now giving you a little bit more information than the previous one because we're now given information about states. But we're expected to use state symbols in our answer. So let's look at that. Aqueous iron 3 nitrate. So again, you'd have to go to your periodic table of ions if you're not familiar with nitrate, which is a polyatomic ion up there. Maybe, well, iron 3, you know the charge on it. So iron 3 nitrate, so that'll be NaFeNO3. Iron nitrate has a charge of 1 minus, so the 1 will go to the Fe. It's Fe3 plus, so we're going to have a 3 there. And it's aqueous, so that'll be AQ plus solid potassium metal, so we have K, and that's a solid. Right, K is the symbol for potassium, which you can see on the periodic table. And that's going to produce aqueous potassium nitrate, so that's KNO3. AQ. Again, NO3 minus, if you look on your periodic table of ions, has a charge of -1. Potassium has a charge of +1. Cross them over, and you get 1 potassium. And if you put the brackets around the nitrate, you'd have 1 nitrate, except we don't need them because if there's 1, you don't write the 1. And iron metal. So that's solid. Whoops. There you go. Solid iron, right? All your metals pretty much are solid, with the exception of mercury, which is a liquid at room temperature. All the other metals are solid. That probably is not going to come up. Okay, so that is a symbol equation. Again, it's not balanced if you know anything about balancing equations. but this gives you an idea of how to write things as symbols, how to use pluses, how to use arrows, and where to put the state symbols and how to use them. All right, we've got one last example. Hydrogen and oxygen gas are combined to produce water. An explosion occurs. Hydrogen and oxygen are diatomic. So what this is telling you is that hydrogen and oxygen fit into this. When you say diatomic, diatomic means two atoms, and that means that in their natural state in the world, you don't have H, you have H2. You don't have O, you have O2. So that comes out of this list. And I'm not going to expect you, by the way, to know this list. I'm going to tell you if something is diatomic or not. But this is just here for your own interest. Okay, so hydrogen and oxygen gas. So that's going to be H2 gas because it's diatomic. And it's going to be oxygen gas. Oops, so that'd be O2 because it's also diatomic gas. And that's going to produce water. Now, I actually don't tell you what state the water actually is. And this can be a bit confusing, actually, because you'll see this in combustion reactions and other things. Some sources will write water as a gas, and some will write it as a liquid. If it's at room temperature, it's a liquid that will be produced. However, probably if you're doing this kind of reaction or a combustion reaction, the heat from the reaction is going to immediately convert that water into gas, right? If you're burning a fire, you don't see water coming out of the flames because the water is vaporized, right? The heat of the flames is so hot that the water produced is turned into gas. So you might start with liquid water, but it will quickly become gaseous water. It's just that that's a physical change, right? When you turn liquid water into gaseous water, that's a physical change. So that might not be shown in this reaction. It might be shown here as a liquid, but you will see both, and I'm not really that picky about either. The only other thing to put here is we get an explosion, so we know that we have a release of energy. And I believe that is it. That's my last example there, where I put in energy. Oh, there's one more example. Ethane, CH4, Rex. Okay, yeah, I'll do this one really quick. Okay, so don't worry about ethane and where that name comes from. That's why I give you the formula. So CH4, which is a gas, reacts with oxygen gas, which we already know is diatomic. There's 2 there. And it produces carbon dioxide, gas, and water vapor. So this one is telling us the state of water. Heat and light are also released, so we need energy. And if we're going to write this in a word equation, we would say ethane plus oxygen to give carbon dioxide plus water plus energy. There we are. And I think that's it. Yep, we've said that energy can be in the products or reactants. So if you produce energy, if energy is released, then you put that in the products. If the reaction requires energy for it to happen, then you put that in the reactants. Okay, so yes, that's everything that we have there. So just to summarize, learning goals here. At this point, you should be able to understand what a chemical equation represents, right? So a chemical equation is showing you how ionic or covalent bonds break and are formed in a change, right? So that's the difference between a chemical and a physical change, or a chemical reaction versus a physical change. In a physical change, H2O is still H2O. You're not breaking any covalent or ionic bonds, or at least you're not changing. You're generally, we'll just say for now, you're not breaking any ionic or covalent bonds. You're not doing that at a large scale anyways. So the H2O that you have as solid, if you melt ice, it becomes liquid H2O. If you rip a piece of paper, the cellulose that the paper is made of, the formula for that is still going to be the same when you have the 2 pieces of paper. But in a chemical reaction, you are breaking and forming chemical bonds. And you're producing new substances, right? Sodium and chlorine and sodium chloride. All of these 3 substances are very different. Even though sodium chloride is made of sodium and chlorine, it's not anything like sodium or chlorine. If you eat either of these 2 things, you will die. If you eat this, it tastes nice. So they're clearly not the same chemicals. They're very different. So chemical changes create new substances by breaking and forming ionic and covalent bonds. You should be able to show what that looks like in a word or a symbol equation, including those that use state symbols or energy. Okay, so that's everything for this lesson. Thank you.